Okay, so this is a video explaining what is Kc and what does Kc tell us. So what I've set up here is a really simple equilibrium. Gaseous A reversibly goes to gaseous B. And I've written out the Kc expression for that equilibrium, so products over reactants raised to the power of their molar ratio, which in my example is 1 and 1. Let's just double check, are any of these things solids? No, that's good, because if they were solids, remember we wouldn't include them in our Kc expression. They're both gaseous, so we'll include them both. I've also set up on the left here a little sliding scale, and on the left hand side of this scale we have 100% reactants, so 100% A in my example, and no products. And then that slides all the way across to no reactants and 100% products. So that would be all B. Now, what this sliding scale here is the position of equilibrium. The position of equilibrium will tell you at equilibrium what is your relative ratios of reactants to products. So what is Kc? Kc is essentially an expression of the relative concentrations of your products and your reactants raised to the power of their molar ratios. So it's all about relative concentrations. That's what those square brackets mean. They mean concentrations. Now, what can Kc tell us? Well, let's say I was to increase my concentration of B. Just take a second to have a think, because of maths, what will that do to our final answer, to Kc, if I was to increase the conc of B? Well, it would increase our final answer, it would increase Kc. So if we increase the concentration of our products relative to our reactants, this is all relative, that means your final answer Kc will increase. Let's have a look at how that plays out on our sliding scale here. If, let's say, I started off with an equal amount of each, right? Let's say I had 50% reactants, 50% products. If we increase the concentration of our products, you're going to start having more products than you are reactants, and so our scale will slide to the right. Okay, so when you increase the concentration of B relative to A, what you're at equilibrium, this is at equilibrium we're talking about, Kc is the equilibrium constant, what we're saying is that the position of equilibrium will lie to the right. If I was to do the opposite, if I was to decrease B or increase A and therefore have more reactant concentration than product, that would mean our position of equilibrium lies to the left. So let's think about this in reverse then. If we find that Kc is a really, really large number, much greater than 1, and Kc can be massive, so let's say Kc is 1 times 10 to the 7, so a really huge number, that means Kc is really large, which means at equilibrium you must have had a much greater concentration of products than you did reactants. So when Kc is much greater than 1, you have more products concentration than you have reactants, and that means the position of equilibrium lies to the right. So when Kc is much greater than 1, that tells us the position of equilibrium lies to the right. It essentially means that at equilibrium your conc of products is greater than your conc of reactants. But that is what the position of equilibrium lying to the right means. Conversely, let's say we just set this equilibrium up again. Let's say my concentration of reactants was much greater than my concentration of products. Well, that would mean my position of equilibrium lies to the left. And if we think about the maths of that, if you increase the bottom term, that's going to make your final answer smaller. So you'll get a Kc value much less than 1. So when Kc is greater than 1, your conc of products is higher and your position of equilibrium lies to the right. When Kc is much less than 1, your concentration of reactants must be higher and your position of equilibrium lies to the left. So in conclusion, you can tell where your position of equilibrium lies by checking whether Kc is either greater than 1 or less than 1.